In this video, I'll be talking about the poster I'm presenting based on this work I put in June 2024. It's titled Proper Time to Singularity and Thermal Correlators. The primary objective of this paper is to understand certain geometrical aspects of the ADS safety correspondence. In particular, I want to know whether black hole singularities are encoded in the CFT side or any such signature of the black hole singularity is encoded in the CFT side. One particular signature can be the proper radial time that it takes for an observer to fall into the singularity from the horizon. For instance, in the black brane background. This is easily computable in the classical GR kind of computation, and one can ask whether the CFT knows about this. Now, in a paper by Greenberg and Maldacena, it was realized that the thermal one-point function of an operator of large conformal dimension does contain this information. In fact, they showed that it takes this exponential form where the exponent carries the signature of singularity, where this mass is related to the large conformal dimension. A follow-up paper by David and Kumar verifies this computation for a number of black hole backgrounds, not just the black brane. The primary assumption that goes into both these papers is a bulk curvature coupling of the dual scalar, and this curvature coupling is shown in equation 8. One can then see that this coupling sources the thermal one-point function via the following Witten diagram in figure 1. And the contribution of this Witten diagram is simply a boundary bulk propagator weighted by the Weil square term and integrated over the full Euclidean geometry. The propagator itself can be computed in the WKB limit, and it takes the following form where it depends exponentially on the geodesic distance from the boundary to the bulk point W. And this entire integral can be performed in the saddle point limit. It turns out the saddle itself lies close to the singularity, and hence it picks out factors of time to singularity. Now, what I have done in my paper is to generalize this entire result to higher point correlators. In particular, I compute endpoint functions and other higher point functions, which are often dubbed as the heavy light correlators, which are correlators between operators of high conformal dimension with order 1 conformal dimension. And the result is that both these correlators do indeed contain the factors of time to singularity as well. And all that is necessary to get this computation correct is that there will be holographic sourcing for both these correlators. And the kind of sourcing I'm talking about can be seen in equation 7, wherein I assume a self-interaction term of the dual scalar and an exchange interaction between the two dual scalars, 2 O phi and O chi. Now again, in the large mass limit, the propagators for the phi field can be obtained in using WKB approximation, and these then we can realize that this interactions in equation 7 shows the higher point functions by the Witten diagram shown in figure 2 and figure 3. The Witten diagram contributions can then be evaluated in the saddle point method, and it so happens that the saddle again lies close to the singularity, and then there appear factors of singularity in the computation, and there are n factors of singularity in the endpoint function as well as capital N factors of time to singularity in the heavy light correlator. And this is just a result of using the WKB approximation and evaluating the bulk integrals in the saddle point.